Hey folks, in this video we're going to talk about 1.12 day 2, which covers transformations of functions in different forms. Specifically in this video we're going to look at transformations with tables and equations. All right, so on this first example, we have a table that shows the function p of x, where the function p is a cubic polynomial. So given a table, we only have a few selected values that we can use. And then it says, let function m of x equal -3 times p of x plus 4. So our first task is to describe the transformations of the function p that led to the function m. So I'm going to look at what has changed about the function p of x, and I notice 3 different transformations. Now on the outside of the function, I have this -3, which is actually 2 different transformations. I have a vertical reflection, and that's shown by the -1 being multiplied on the outside. The 3 being multiplied on the outside is a vertical stretch of 3. AP likes to call stretches end shrinks dilation, so if this were a multiple choice test, on the AP exam you would probably see the phrasing a vertical dilation of 3, or a vertical dilation by a factor of 3. On the inside of the function, I see this +4, and I know that transformations on the inside are going to be horizontal transformations, and they're always going to be the opposite of what I expect. So the +4 on the inside is going to be a shift, and that's going to be a horizontal shift to the left. We want to be as descriptive as possible, so I'm going to say a shift to the left 4 units. Want to be able to say how far. You can say horizontal shift to the left, that's totally fine. I think the word left indicates that it's a horizontal shift, but if you wanted to be extra descriptive, you could add in the word horizontal. All right, now we're going to find some values. So it says first, find or name an x value where m of x has a 0. So that means we're looking for an x-intercept where the y value is a 0. So we're looking for where m of x is equal to 0. Now, the only thing that I have to go off of with m of x is its relationship to the function p in the table. So I'm going to plug in the expression for m of x in terms of p. Right, and I'm going to solve that like an equation. So if I divide both sides by -3, 0 divided by anything is going to stay 0. So I have this statement, p of x plus 4 is equal to 0. So I'm going to look on my table, where is function p equal to 0? And I see right in the middle there, when x is equal to 2, our output for function p is 0. So p of 2 is equal to 0. So that means I want x plus 4 to equal 2. And I'm solving now backwards to figure out what should that input be so that the inside of that function p ends up equaling 2. And I want it to equal 2 so that the output ends up equaling 0. So if I treat this like an equation, I subtract 4 from both sides, I get x is equal to -2, which would be my final solution. Okay, and thinking about it in terms of transformations, right, the original x value is 2, that shift to the left 4 would lead us to a final x value of -2. Last one here is fun. This brings us back to the beginning of Unit 1 with rates of change. It says find the average rate of change of this function m over the interval 0, 2. Now remember, these are x values, so on the domain I'm looking at the window from x equals 0 to x equals 2. And I know that average rate of change is finding the average slope between those 2 points. So I'm going to set up my slope formula, m of 2 minus m of 0. That's my change in y over change in x, 2 minus 0. Okay, again, function m I can only describe based off of function p, so I'm going to think about plugging that set of x values into function m. to find those y values. So I'm talking about the numerator of this average rate of change difference quotient. So thinking about if I plug 2 into this equation for m of x, I would get -3 times p of 2 plus 4, which will give me 6. And then when I plug in 0 into that function, I would get -3 times p of 4. And then in my denominator, 2 minus 0 gives me 2. So looking at my table now, I'm going to find these two values, p of 6 and p of 4. They're at the end of my table, the last two columns. So I'm going to take -3 times p of 6, which is 7, minus -3 times p of 4, which is 3, all over 2. So that gives me -21 minus a -9, so that's going to be plus 9 over 2, which is -12 over 2, which simplifies to -6. A few more questions about this same table and same set of functions. It says find the domain and range of our new function m. So in order to find the domain and range, I'm going to look at the domain and range of the table. And it doesn't really tell us if this function p has values outside of the table. So based off of the context and the information we're given, we're just going to assume that this gives us the full kind of spectrum for the domain and range. So for the domain, my values go between -2 and 6, including both -2 and 6. For the range, it looks like this minimum value is -1, and the maximum for the range is going to be a +7. All right, so I'm going to answer the domain and range of function m in thinking about our transformations. Now for the domain, all horizontal transformations are going to affect my domain, and again, I'm moving left 4. So the beginning of my domain, that lower bound, is -2. To move it to the left 4, I'd have to subtract 4, the opposite of what I see. So my new domain is going to start at -6. If I do it for the upper bound, originally that maximum for the domain was 6, move it left 4, subtract 4, I get 2. So my new domain is going to be from -6 to +2. Now for the range, I'm looking at the vertical transformation. So I have this vertical flip and stretch, or reflection and stretch. And that stretches by a factor of 3. So for my range, let's see, I'm starting at -1. To flip it, I'd multiply it by -1 and then stretch it by 3. I'm going to end up with, let's see, -1 times -1 times 3, +3. Same thing for the upper bound, 7 times -1 times 3, I get -21. Okay, now when I list these, I have to go from least to greatest. So the upper bound of my original range ends up being the lower bound of my new range for function m. Because of that flip, -21 is less than 3, so that has to be listed first. Okay, and then 3 is going to be the upper bound, so I'm going to list that second. For the last one here, we have a question similar to one that we did on the last slide about finding specific values for function m. Last time we did zeros. Here it says, where does m of x equal 3? So plugging in my expression involving p, I get -3 times p of x plus 4 is equal to 3. Now if I divide both sides by -3, I get p of x plus 4 is equal to -1, and I want to look at my table to find where that's true. And I find that when x is 0, p of 0 is equal to -1. So I'm going to kind of work backwards to solve for x. Now x plus 4, I want to equal 0. Right? Or thinking about it from a transformation standpoint, I have this x value of 0 that I need to shift left 4, so I'm going to subtract 4 from both sides, and I get an x value of -4. All right, moving on to transformations with equations. So here I have function f of x, and I have the full equation, and I know g of x is equal to f of negative x. So because I know the relationship between these two functions and I have the full equation for f of x and not a table or a graph, I'm going to go ahead and find what function g of x looks like. And I'm going to do that by plugging in negative x into function f. So that will give me negative 2 times negative x plus 3 squared times negative x minus 1. Okay, and I'm going to use that function g of x, that equation, to answer these questions. So first it says, find the zeros of g of x. Okay, just like we did in our polynomial unit, I'm going to set each of these factors equal to 0 to find those zeros. Now that negative 2 out in front, if I think about setting that equal to 0, negative 2 equals 0, that doesn't give me a solution, so that's not going to give me a 0 of my function g. If I set negative x plus 3 equal to 0, I get negative x equals negative 3, so that means x equals 3 is a 0. Last factor, set that equal to 0, negative x equals 1. That means I get zeros at negative 1 and positive 3. Next one says, on what intervals is g less than 0? So this is our inequality. There's a couple different ways that you can solve this. I like to solve our polynomial inequalities with a quick sketch of the graph. So that means I'm going to take these zeros that we found above and put them on a number line, thinking of that as my x-axis. Okay, and I know based off of the multiplicities that at positive 3, I'm going to have a bounce. And at negative 1, my multiplicity is 1, so I'm going to have an x-intercept that crosses through. The other piece of information that I need is the end behavior. So I'm going to look at the leading term of g of x, and I'm going to do that by multiplying the first part of each factor together. I can't forget that negative 2 on the outside would also multiply into the leading term. So I'm going to have negative 2 times negative x squared times negative x. So that would multiply out to give me a positive 2x cubed. So that means the right side is going to point up and the left side is going to point down. So quick sketch of my graph, left side down, right side up. Okay, cross through negative 1, bounce at positive 3. And I'm going to use that to now solve my inequality. It says, where is g of x less than but not equal to 0? That would be just the far left portion of my graph, because after that everything is at 0 or above 0. So my solution is going to be from negative infinity to negative 1, not including negative 1 because I don't want to include the 0. Taking a look at a couple of similar questions, but now be careful, we have function h, which takes that same function f, but it changes it a little bit differently. This time we have h of x is equal to 2 times f of 3x, so we have a vertical stretch by 2, and we have a horizontal compression or shrink by 1/3. Remember, those horizontal transformations are opposite of what you expect. So we can kind of approach this the same way as we did before, where we plug in those values into function f to find function h. So if I do that, h of x is going to be equal to 2 times my function f, where the input instead of x is going to be 3x. So I'm going to simplify that outside to make that a negative 4. And this is what my equation for h of x would look like. Now it says find h of 1. So I'm going to plug 1 into my expression for h. I get negative 4. This would be 3 plus 3. That's going to give me 6 squared. And then if I plug in 1, 3 minus 1 gives me 2. So I have negative 4 times 36 times 2, which is going to give me negative 288 as my output. Next question says, on what intervals is h of x greater than or equal to 0? So similar to the one that we did on the last slide, we're going to build a quick sketch of the graph. First, we have to find our zeros. So I'm going to set these factors involving x equal to 0 and solve. I get a 0 at negative 1 and 1/3. Okay, now you can plug in values in these intervals to see if the output is positive or negative, or you can sketch a quick graph of the function. In the case of polynomials, I prefer to do a sketch rather than plug in values. To do my sketch, I need to know the leading term to find the end behavior. So that's going to be negative 1 times 3x squared times 3x. So let's see, that coefficient is going to be a negative. I'm not worried about what the number is. I just need to know if it's negative or positive for the coefficient. And then I'm going to get x cubed. So that means the right side is going to point down, the left side is going to point up. I have a bounce at negative 1 and crossing through my function at 1/3. Now, the intervals that I want are the intervals where it's equal to 0, so I'm going to keep these zeros, and where it's greater than 0, so that means the part above that x-axis. So my solution is going to be everything from negative infinity up to 1/3, and I'm including 1/3. I want to write that as one full interval. If you write it as two separate intervals joined with a union, AP would say that that's not simplified. Last one here says, what is the y-intercept of h? Now I have to remember that every y-intercept has an x value of 0. So to find the y-intercept, I'm going to plug 0 into my function h. So that's going to be negative 4. If I plug in 0, I'm going to get times 3 squared times negative 1. So that's going to be positive 4 times 9, which gives me a y-intercept of 36. And you can either say the y-intercept is 36, or you can write it as an ordered pair, 0, 36. All right, my last one here is a rational function r that has been changed into function k with several different transformations. Because there's a lot of transformations in k, I'm not going to plug those transformations in and get a new equation for k. I'm just going to kind of think about it from a transformations perspective. Okay, on the outside are vertical transformations here. I see both a vertical reflection, that negative 1, and I see a stretch by 4. On the inside, I have two horizontal transformations. I see a reflection, and then I see a stretch by 2 because I'm multiplying 1/2 times x. So my first question here says, identify any x values where the graph of k has a vertical asymptote or a hole. So what I'm going to do is look at my original function r, find where that had a vertical asymptote or a hole, and then transform those locations based off of what I see in function k's statement. So starting off with the hole, I'm going to look for factors that match, and I see these matching factors of x minus 3. So that means r of x, my original function, has a hole at x equals 3. So I'm going to transform that based off of the transformations that would affect the hole. Okay, now I'm just looking at the x coordinate of the hole, so I'm just going to look at these horizontal transformations, right? Setting it up like an equation, there would be a hole when r of x, where x is equal to 3, so that would be r of 3. So that means negative x over 2 needs to equal 3. So I'm going to multiply both sides by negative 2. So I get x is equal to -6 would be the location of the hole. Now I don't need to find the y value in the statement. The question, it just says find the x value, so I don't have to worry about finding the y value. I'm going to switch and now look at vertical asymptotes. I see that my original function has a vertical asymptote where this factor on the bottom, x plus 4, doesn't have a matching factor in the numerator on the top. So that means r of x has a vertical asymptote at x equals -4. Okay? So I need the input to equal -4. So in function k, that means -x/2 has to equal -4. Multiplying both sides by -2 gives us the new location, which would be a +8 for x. So there's going to be a new vertical asymptote at x equals 8. The last one here says, where is k of x greater than or equal to 0? So because I haven't created a new function equation for k of x, I'm going to solve this based off of the relationship between k of x and r of x. So I have this statement, k of x is greater than or equal to 0. Okay, and I know that k of x is equal to -4 times r of -x/2. So my statement now looks like this. All right, so if I rearrange that as best as I can to solve for r of x, or get r by itself, I'm going to divide both sides by -4. And I have to remember that when I divide by a negative, that's going to flip my inequality. So I have r of -x/2 is less than or equal to 0. Now I'm going to set up this inequality statement looking at function r. I'm going to look where r of x is less than or equal to 0. So I'm going to do that with a sign diagram. On my sign diagram, I need to put zeros, vertical asymptotes, and holes. I already have the hole and the vertical asymptote. I solved that in the one above, +3 and -4. I also need the 0, which, looking at my original function, it looks like we have a 0 at -1. So I'm going to put -4 for the vertical asymptote, -1 for the 0, and +3 for the hole. I'm going to test each of the intervals on this sign diagram. Looks like we have 4 of them, by plugging in x values and finding if that output is going to be positive or negative. So in that first interval, I'm going to plug in -5. Let's see, if I simplify function r, I'd get x plus 1 in the numerator over x plus 4 in the denominator. So plugging in -5 would give me a negative over a negative, which makes that first interval positive. I'm going to continue to plug in other x values for the other 3 intervals. Next, I'm going to plug in -2. You can plug in any number in between -4 and -1. If I do that, I would get a negative over a positive, which gives me a negative interval. In the third interval, I'm going to plug in 0. That would give me a positive over a positive, which gives me a positive interval. And then in that last interval, I'm going to plug in, how about 5, which gives me another positive over a positive. So I have positive, negative, positive, positive for those intervals from left to right. Now, looking at this inequality that I'm trying to solve, I want where my function is less than or equal to 0. So that's just this section between -4 and -1. Okay, the or equal to 0 is going to also include the 0 itself at -1. So my solution, like where r of x is less than or equal to 0, let's see, would be on the interval, let's see, -4 is not included, -1 is included, so it would be from -4 to -1, square bracket on -1. Okay, so I want to kind of translate that to k of x. Okay, thinking about my transformations. Now, where would that x value of -4 move to? Okay, so I have -4 is equal to this statement, -x/2. So if I multiply both sides by -2, I get a new x value of 8. If I do the same thing for the upper bound on that -1, which would be x, and I want -x over 2. Multiplying both sides by -2 gives me an x coordinate of +2. So my solution for k of x, right, originally we were looking for where it's greater than or equal to 0 before we undid some of those vertical transformations, would be from +2 to 8. Okay, the +2 is included because that was the value that came from the 0, the -1, where the 0 moved to. 8 would not be included because that's where my vertical asymptote would be, and I never want to include the vertical asymptotes as part of my solution.